a theme that came up a couple of years ago at the Mars Society conference was we kept circling back to the word feckless, which means somebody who pretends to be doing something but never actually gets anything done. And as you probably read in the description of this talk, I basically said that a grand challenge is something that the government can spend $1 billion in 10 years on and only move the ball 10% before asking for the next 10 billion or whatever. So what we're trying to do is focus on the barriers to space settlement and come up with designs that are affordable, integrated, modular, have near-term revenue potential, and also evolve into practical solutions for long-term settlement prospects, and offer more than one critical path. By that I mean, if God forbid SpaceX ever has a major problem, it's not the end of the world. If God forbid Bigelow Aerospace has a major problem, it's not the end of the world. We're not stuck in one. There's no single point of failure in this system. Next slide. This is something that was originally created by, it's cut off at the top, but that was originally created by Rockwell back in the early shuttle era. And it's called the Integrated Space Plan. And it's supposed to go out 100 years. And it starts, everything on the critical path starts up here with the shuttle. And then all this stuff is supposed to happen when we have cheap launch. And there's like Venus terraforming down here and Mars terraforming over here and starships and all this stuff. And then this is just a detail of the middle of that, where, of course, everything starts with the shuttle and goes to the space station and on down. And does this look focused to you? It doesn't really look all that. It just looks like a great way to spend lots and lots of money. Next slide. I've identified about 20 or so grand challenges, and I've grouped them into 4 sets. One is just getting into orbit affordably. Next is crewed missions beyond Earth orbit, Moon and Mars landings and bases, and then just universal issues, which were, they're more annoyances than barriers, but the difference between an annoyance and a toxin is dose. So they can be bad if they're out there long enough. Next slide. So the first group is affordable launch, which SpaceX is doing. I've got it broken down into, this is what the challenge is. This is roughly where we're at. Who's the standard bearer of actually fixing this, and do we think this is going to be solved by any particular date? So affordable launch, SpaceX is doing a lot. Other new space companies are following suit. Large launch, in other words, anything over 100 metric tons. I think Mars Colonial Transport by SpaceX, again, is probably our best bet there. No offense to the last guy in the main session. Mass fraction beyond Earth orbit. In other words, if you could launch 100 tons into Earth orbit, you could only get 25 tons of that to Mars. So how do you get past that? How do you leverage that to kick it up a notch? Space junk is actually a negative trend, because the more time goes on, the worse it gets. One of my thoughts when Project Constellation was originally announced is maybe the reason they want to go to the Moon and Mars is because Earth orbit's getting really dangerous. And at the time, the stats on the space station were that it had about a 1 in 6 chance of a catastrophic failure from space debris over the course of a lifetime up to about 2025. So maybe the idea was, let's get out of the shooting gallery and hang out on the Moon where it's safe. Microgravity, NASA has done a lot recently where they've got a combination of medication, diet, and exercise, and they've pretty well reversed or halted the calcium loss in bones. And that was a very, very big deal. That's part of the reason they're talking about going to 1-year missions for people on ISS. However, we'll get to another challenge on the next slide, which may cause an issue with that. And then Mars Society has done a lot with the idea of let's do a centrifuge type arrangement. Reusable vehicles to orbit and beyond orbit, again, SpaceX is our standard bearer. Next slide. So group 2 is beyond Earth orbit. Solar flares we can block with 10 or 20 centimeters of water. Bigelow talks about putting water in the outer shell of their inflatable habitat, so they're probably the standard bearer on that. GSR is galactic cosmic rays. There's actually several hazards from this. One is the obvious of cellular damage of it hits something that, basically it hits with the force, a really powerful cosmic ray hits with the force of a baseball at 50 miles an hour, which, if that doesn't sound too bad, is like, okay, now put a needle in front of that baseball. Now make that needle the size of an atom, or actually a nucleus, and then drive it through your body. And odds are it's not necessarily going to hit anything, but if it does, and there's a cascade effect, I mean, this is called cosmic rain when it comes through the atmosphere. There's this whole lightning bolt of cascades of mesons and so forth being kicked off from one particle to another. So it may not be the bullet, it might be the shotgun blast of all the, that comes between you and it. And there are certain parts of the body that are very delicate to that sort of damage, and there's other parts that, I gave the example yesterday, there's a 1 cubic centimeter thing called your hypothalamus, which is a really critical part of your brain that converts long-term and short-term memory. I'd be a lot more worried about a cosmic ray hitting that than, say, the end of my finger, which is exactly the same surface area or volume of human flesh. So remember how we said that they've worked out a solution with medication and diet and everything? Well, the other thing radiation does to food and to medication is it makes it expire a lot faster, because it's breaking down all the nutrients inside the food, and it's breaking down the active ingredients inside the medications. So if you do a 3-year mission, are you going to have issues with that? Interestingly, this was the same problem they had 300-400 years ago with vessels visiting the New World from Europe. They had an issue with food preservation on multi-month voyages. The whole thing was scurvy and so forth. So I remember reading the original journals of, I think it was Cabot, and what they did was they came into roughly New England, and the first thing they did after they went into the forest and grabbed wood to rebuild the ships and so forth was they planted a garden. And this was spring, and they hopped their way down the coastline and did their explorations and everything, and then they hopped their way back up the coastline, and in the fall they harvested the garden, set up the food and preservation, whatever they had there, drying or whatever, and they used that food for the trip back. So on Mars, if we have an issue with food preservation going to Mars and having the same food be good on the way back, maybe that's a driver to have a greenhouse set up on Mars to get fresh food for the return voyage. And then medication I'm not sure about, but of course there's always the centrifuge. Mechanical and medical entropy, in other words, things break down, rust never sleeps, things are going to break over time. We had a little bit of talk about that yesterday with modular solutions. And then the psychology of 500 days in a minivan with somebody you better really like. Next slide. So this is, group 3 is landing on the surfaces, moon landing, it's kind of being reinvented now. Mars EDL is a huge challenge for right now we can land a ton, we need to be able to land at least 25. Spacesuit tends to, we're talking about going to Mars for 500 days, but we've never made a spacesuit that's lasted more than a week and, lunar grit, and they always come back with, grit in the joints and so forth. And anybody who's been to Mars Desert Research Station is probably still getting grit out of their camera and their laptop at this point. Reliable ascent vehicle, it better be ready to run when you're ready to go. Otherwise you're going to miss your window, and that's the least of your problems. Reliable return vehicle on orbit. In other words, if your Earth return vehicle is in orbit, it better work when you get there. Kind of mature technologies. I mean, we've done rovers for 10 years now, so maybe it's not that bad. And then flight to Earth and Earth reentry are pretty well mature. Next slide. And then these are just the new ones, flight time, universal issues, launch windows, because it's, you can stay on Mars for 14 or 500 days and practically nothing else. Temperature ranges, sunlight drop off, there's 40% as much light at Mars, so you have to have more solar panels and so forth when you get there. And then just the speed of light in terms of communication. Next slide. So if we graph this out in terms of danger versus technical challenge, this cosmic ray health issue is probably the elephant in the room. These things are more inconveniences. They're not necessarily going to hurt you. They're just going to cost money. Spacesuit lifespan. Space junk's kind of a big deal. Solar flares are a very dangerous thing, but a very solvable thing. Microgravity is kind of in this camp and so forth. And the color on these slides, these were things we touched on with that mini mission module solution yesterday. And then today we're going to just talk about everything. Next slide. So what we're trying to do is go from being observers, these detached people living on Earth who look at the skies and kind of go, ain't that neat, to explorers. And I think the best definition of an explorer is somebody who actually goes somewhere and comes back and does not look at the world the same way as they did when they left. As I say, if you go to MDRS for 2 weeks and you come back and you're exactly the same person as when you left, you're doing it wrong. because that much of a change in environment should do something to you at a very fundamental level that makes you, if not a better person, at least a different and more mature individual. And then settlers are people who go there once the basic dangers are known, and you have to have basically a mitigation knowledge of the environment. In other words, can I go there and have a reasonable chance of coming back? It's a test pilot mentality. Practical knowledge is more in the space tourism camp at the explorer level, and then settlers is we've probably reduced the danger down to that of an airliner. Next slide. Speaking of airliners, that was when my dad was a test pilot on the B-47, which was the forerunner of the 707. They had a tendency to blow up midair and so forth, and he felt that there was absolutely no way, given the level of training he had as a test pilot on that there would ever be such a thing as a jet airliner. Because back then it was like flying a shuttle. We talked about, this was a slide from the previous talk as well. The idea is that you take our better knowledge that we've had in the last 5 years of cosmic rays based on the AMS on the space station, the Mars Science Laboratory experiments. We take our modular designs over here, we feed all this stuff into a computer model that does ray tracing, then we take a volumetric model of here's how much volume I have in food, this is how much volume I have in crew, this is how many hypothalamuses I have to worry about and the cubic centimeters on that and so forth. And we do a very detailed risk assessment of every design. And if the design is modular, then we can rearrange the modules into something else that works and run the simulation again. And eventually we will find the safest possible configuration of that vehicle. Next slide. So first mission concept, we need to say, okay, what are we going to do? Break it into simplified modules, find other uses for those module combinations. In other words, if I rearrange the Legos, what am I going to get? Like when the Model T Ford came out, everybody was like, wow, it's a vehicle that goes 30 miles an hour. It needs a truck bed, it needs a this, it needs a that, and it ended up morphing into all kinds of different things, fire trucks and ambulances and every other thing. We match the inputs and outputs from module to module, identify cost-effective improvements, and then determine the next modules for the next expansion. Next slide. So we kind of saw this with SpaceX when they went from the Falcon 1 to the Falcon 9 and then on. We identify the current pain points. Launch is expensive in their case. We develop a modular solution set. There was a programmer interviewing Elon Musk who knew him from his PayPal days and basically said, this is a rocket designed by a programmer because it's all modular, all the engines are iterate in step. Then we come up with a minimal solution that will do something that is a proof of concept, which was what the Falcon 1 essentially was. Is let's prove we can actually make a rocket, and then we'll immediately turn around and make a bigger rocket. And we're doing it with minimal risk and minimal investment. We gain a revenue stream. We expand the market base by lowering the cost. In other words, the supply and demand curve. If you lower the cost, you increase the demand for the product, which leads to mass production, which leads to lowering the cost even further, and so forth. We roll the profits into development of updated modules, and then we go back and say, okay, this is the new world. What are our new pain points? Next slide. So focus is on early monetization, because if this thing doesn't pay for itself, nobody else will. Space is great, but the world seems to see it as a nice to have instead of a must have, despite raising like $500 billion in revenue every year nowadays. Current near-term pain points, lower development costs, existing and near-term technical challenges, and industries with high growth potential. Next slide. So the thing I've noticed with CubeSats, for example, is they're either too small because I can put 3 together, but that's not a communication satellite, or they cost as much as a good-sized house, so it's too big, I can't afford a whole CubeSat. Well, what if I, okay, so these are the challenges and the parameters. I'll come to the solutions on the next slide. Geosynchronous communication satellites are underpowered, expensive, short-lived, and risky. Actually, they're really good at all of those things because we've spent so much money on them for so many years, but if you're making, I think we're up to 150 billion in revenue worldwide on communication satellites alone. If you're making that kind of revenue and you can make it twice as much, by doubling the bandwidth, doubling the reliability, making it modular in some way to make it work, then what do we do from there? Space junk and so forth. We're going to have to blow through this because we're down to 10 minutes. because we started late. And then near Earth orbit object mining and so forth. So, next slide. So we move all those over. We can have a rail system for CubeSats where we can take, okay, I'm going to put all your power and your data on a rail. And you can run your CubeSats down one side, and then if your package is too small, we'll just make a cheap thing, put it on the end. If you need something that's too large or whatever, all your power and data is taken care of. Let's put it on a framework. Let's make those frameworks in geosynchronous orbit for the next phase and be able to make modular communication satellites where we can swap out modules as they become outdated because of Moore's law. Or we can swap out the solar panels because solar panels decay on orbit in about 5-10 years, so forth. We have a space tug to go up and do those servicing missions, satellite servicer, space junk collector. We can do a proof of concept to try and at least get the kick stages out of orbit. Next slide. So we're going from that to, we still have the issue of expensive launches. Maybe we're going to get that down with Falcon Heavy. We've still got the satellites, we've still got the space economy issue, we've got other risks going on in the world between now and 2020, and we're going to try and do things to mitigate. We've got drivers for asteroid mining, beyond Earth orbit crewed flight, and satellite launch. Next slide. So let's break this into a modular system of low Earth orbit frameworks and so forth, and all these places. Next slide. And so when we break it down, we've got these modules with these parameters. Remember how I said we need common inputs and outputs, so your solar panel is putting out the right amount of power for your other modules. Next slide. Small and inexpensive crew habitats would be our next thing. Space junk collection, crewed missions beyond 500 days in space, so forth. Next slide. So now we have a new set of modules that involve filling things with water and so forth. Next slide. We're going to have to fly through these. This was a design I showed in 2011, and then I stepped it up to this in 2012, where we take, initially it was a modular set of ice-filled containers that would all inflate off of the thing. They'd be filled with water from a tanker based on a Falcon Heavy. And basically this had enough delta V on paper that it could go out to Mars orbit. It would empty the tanks in the process, so it wouldn't be much of a refueling station, but if you have it in Mars orbit, then you can bring the fuel from Mars or from Phobos. Next slide. So this was the original. I've come up with some hybrid tanks. These are water on the outside, or ice actually, and then a small tank in the middle, and then just a solid tank in the next one. Next slide. And then these are our modules. This is hybrid, just a fuel tank, a thing full of water, actually ice, and then a crew module, which is like basically the size of a 20-foot intermodal shipping container. And then solar panels are scaled to this sort of arrangement. Next slide. So if you're going to take water and convert it into hydrogen and oxygen, liquefy it and do all this, and then they actually make too much oxygen for the hydrogen for a rocket engine, so we take along some methane as well. We mix the rest over there. And when you do liquefaction, that heat's got to go somewhere. When you do electrolysis, that heat's got to go somewhere. We dump it all back into the ice, and we use that as a big heat sink. So we leverage the operation against itself. Next slide. So just masses on everything. So we have a chemistry module, a solar array of 8 of those bits, liquid hydrogen tanks, and so forth, and then the cryo engine block, which is basically the rocket engine for this whole thing. Next slide. So this is where, this is sort of a step iteration thing of you go from, you make enough fuel to fill those tanks, you fire the engines, you make enough fuel to fill the tanks, you fire the engines, and you've got enough ice on board this thing to do 12 iterations. And if you take along enough methane to use the rest of the oxygen, you get up basically to this kind of performance. So if you carry 0 payload on a unit that has 8 solar arrays, 3 liquid hydrogen hybrid tanks, 2 liquid oxygen hybrid tanks, the chemical engine and so forth, or chemistry plant and so forth, you end up with this performance. So with 0 payload, it takes you about 13 iterations to get to Mars orbit, or to a lunar transfer orbit, you're about 10 or 11 iterations. I can't quite see from here. However, if you carry 8 extra methane tanks, or I'm sorry, 35 tons of just raw cargo, you just barely make it to Mars orbit. And if you carry that and you also carry extra methane, you can just barely make it to Mars orbit. It just takes a little longer. So the idea here is if you built this thing and you step it out and it takes you about a week per iteration, you really don't want to be on board that whole time. but you can get it into just about to a lunar transfer orbit, and then just send the crew out on a Falcon Heavy, because it's in this long parabolic orbit, which, by the way, gives you 24-hour sunlight. So you can run the process 24/7. Then, once the crew's there, then you do the last couple of burns and you're on your way. Next slide. So we can do, because of the cosmic ray thing, we don't really know exactly what the cosmic ray hazard is, but we can change. We can have a 3-crew, 3 large tank for a minimal configuration where it's all crew and tanks. We can have some ice barriers here, so we have a storm shelter here, which is about 50% covered with about 3.5 meters of ice around it. Or we can go incredibly paranoid. What I'd like to do is stack this. I'd like to stack this and have this as a bottom layer, then this, and have a biological lab all the way through it at an L5 point, which would also be a perfect refueling point for going on from there, or in L1 or L2 around the moon. Next slide. We're down to 5 minutes. Yes, this is practical, and I used real hardware to come up with the estimates, and they're about twice as bad as they need to be, and so in other words, that curve could be a lot better. Next slide. Next set of modules for doing these various missions, and roughly the count of how many Legos you need to build that particular project. Next slide. Mass for each module. Next slide. And then, so this is our maturity on phase 1 and phase 2. Next slide. And then if we're going to go to a phase 3 and phase 4, these are the other issues we need to solve. Next slide. And then once we get nuclear transport or nuclear thermal rockets, we can take that hydrogen and put it into that loop. This is in Mars orbit. And we can bring up water and dry ice from Mars via surface shuttles. And then we've got all the oxygen and methane for surface shuttles. Next slide. So as I was wrapping up this presentation, somebody sent me this on Facebook, and I thought it was appropriate. Any questions in the little time we have left? Yes?
What kind of materials are being used for the structure?
Okay.
What kind of materials are being used for the hexagonal structures? I wasn't here for that earlier.
The actual frame, and I'm sorry, I actually printed out 3D models of the arrangement. And I'll probably use this in the next talk because I'm going to be talking about something also involving hexagonal prisms. I gave a rough mass estimate based on if it was composite for the frame. The actual bag, I spent about a day iterating exactly how much a Bigelow habitat weighs given everything. So I finally found a formula that predicts how much a Bigelow habitat will weigh for different dimensions than the ones that have been published. So.
Oh yeah, and last question. How wide is the hexagon? What's its widest point for these modules? Now you're going to put them on Falcon Heavy, you said, or Falcons?
Well, they fold up.
Oh, they fold up.
But now the one that's just a pure tank, well, it's 2 meters at the base, so it fits in a Falcon. It fits in a Falcon 9 fairing.
Okay.
And actually, that original design I had, all that folded up inside a Falcon Heavy.
That's really cool.
And that was 7 modules.
Yeah, 7 modules fit.
Right.
That's really cool.
And if they're just crew modules or just water modules, no problem. Any other questions? Okay, I'll turn it over to Alan. Thanks.